Hello, and welcome to AP Bio Review 2.3 to 2.5. So let's begin. See what we got. So in this section, we're going to start with cell size 2.3. And again, we've talked a lot about this. Cells are organized, and they're going to need an input of energy to exchange with the outside world. So let's see what we got. Why are the cells of the intestines long and narrow and not large and cubic? So, the cells are called columnar cells, or they're very, very, very long versus being cubes. Now, a cube seems reasonable, right? But here's the problem. The center of the cube is hard to get to, either from that side or from that side or coming in from that side. And the same can be said about getting the wastes out. So a cube cell is not good. A long, skinny cell is very good because what happens is when stuff diffuses in or out, it does not have very far to travel to get to the center. So that's why the cells of your intestines are long and narrow, not cubes or not circles. Circles are just as bad because check it out. We have a circle. A lot of people said spherical, which is bad. It's columnar. Look at how far you have to go either to get stuff in or to get stuff out. So circles no good, cubes no good. Long and narrow, good. So it's all about the surface area to volume ratio. A lot of you, when you did the math, you either did the surface area or the volume, or you put a question mark. Again, bad. Now, the one thing I absolutely cannot believe that I cut and pasted on your version of this, a formula sheet from the AP thing they sent me. And they actually had the volume of a cube as V equals S squared. So some of you, when you did your math on the FRQ, you messed that up. And I looked at the way you did it. And if you messed it up because of my bad formula, then I gave you the credit because you would have got it right if you would have used the right formula. So I cannot believe that. So on the video, we have the correct version, side cubed. So we will see that coming up. So it's all about surface area to volume ratio. I would say a few of you messed up the fact that if the surface area to volume ratio was big, that was bad. And that's wrong. A big surface area to volume ratio is what you want. That means that the cell is efficient. So be careful on that. A couple of you messed that up. So it is all about, surface area to volume ratio is large. The bigger, the better. Believe it or not, small cells have a large surface area to volume ratio, and long, skinny cells have a good surface area to volume ratio. So let's see what we got. First one, we have a simple cube, and again, if you messed up the math with the side squared, you messed it up. But let's see what we got. Surface area of a cube, and we know it's a cube because all the sides are the same, and the volume of a cube. So in this case, my surface area is the side, which is 1, and I got 6 of them, so it's 6, divided by the volume, which is each side is 1, so 1 times 1 times 1 is 1. Your surface area to volume ratio is 6. That's really, really good. Well, what about this scenario? Here, I made the cube bigger. So now, instead of traveling only a half a centimeter to get to the middle, now you have to travel 2.5 centimeters to get to the middle. That's a big difference. So let's see what we got. We know that each side is 25. That's the area of one side. So you got to multiply it by 6 because it's a cube. So our surface area is 150. If we do the math on the volume, it's side cubed. So 5 times 5 is 125. And your answer there is going to be 1.2. Now, the answer that I sent you guys, I don't know what I was thinking. I rounded wrong on this. 1.2 is correct. That's the right answer. So what's better, a 1 centimeter cube or a 5 centimeter cube? Bigger size of the cell is not better. This one has a better surface area to volume ratio. This one will be better at exchanging materials with the outside environment. What if I do something funky like this? Now this one's kind of neat because if you look, it's big, right? It's bigger than that. This is 5 times 5 times 5. This is 3 times 4 times 10. So it's kind of bigger, but if you notice, it's long. Now long is good because remember, I only have to go that far to get to the middle of the cell. I don't have to travel a huge distance. Now the surface area on something like this is a little annoying. And you have to remember that it is a rectangle. So the area of this side is 40, but you got one on the other side. So there's your two 40s, 40 and 40. The area of this side panel is going to be 30, but you got two of those, so there's your two 30s. And then the area of the top, which is 4 times 3, is going to be 12. You got two of those, there's my 12s. So figuring this out was always a pain in the neck, but my surface area is 164. My volume is very simply 3 times 4 times 10, which is 120. And again, I believe I rounded this one wrong on the answers I sent you too. Again, embarrassing. Here's the answer, 1.37 rounded to the hundredths place. And again, this time I used the surface area of a rectangular solid, and I used the volume of a rectangular solid. So it's different from a cube. But this long and skinny one is better than this 5 by 5 by 5 cube, but not as good as the 1 by 1 by 1 cube. So does that make a little bit more sense? The bigger the surface area to volume ratio, the better. Okay, so why is bigger not better? Because if it's too large, the materials, it's too hard to exchange them with the outside environment and too hard to get stuff into the center and too hard to get stuff out from the center. Well, what if I do a cylinder? Well, cylinders all kind of wacky. And again, you're not going to have time to do this in the real AP test this year, but that doesn't mean if your brothers or sisters take it, and they could. So here, I used my crazy formula to find that the surface area was 2,512. My volume was 9,420. My surface area to volume ratio is horrible. It's only 0.27. So this would not be good. And remember, 10 centimeters compared to the length of 30, that's not a good ratio. That's kind of stumpy and stubby. So that's why the ratio's not good. Okay, so that would be, again, not a great cell. So why is this so important? It's all about exchanging materials. And what will happen is if you cannot exchange materials, that means you can't get in materials fast and you can't get them out fast, and you can actually poison yourself. So let's think about heat, for example. Even though, let's see, for example, that is why cells, even in a large animal like an elephant. So an elephant itself is humongous. So an elephant, when you talk about heat, is going to take a very long time to lose heat from its body because it's humongous. But each cell that makes up an elephant is tiny. So although the elephant is humongous, the cells are small. And it's all about the efficiency of the cells. Now, in the event that you're looking at something like your intestines are going to be, instead of just a regular hollow tube for absorbing, inside of that tube, it's lots and lots and lots of folds. Now that sets up these column-like cells. See, these look kind of like columns. And that's going to allow for a ton of absorption. So that is what it's all about. Folds, and the folds are going to be found in the endoplasmic reticulum, which is going to increase their ability to get stuff in and out, and also in places like your small intestines. So if you look at your small intestines, they are jammed up inside of your abdomen. So that's, this whole pathway, and they're like 30 feet long. And then within them, you can see here how they're very folded. And because they're folded, look at that, how kind of long and skinny they are with your blood vessels smack down the middle. And that allows for a lot of absorption. And those, once again, are called villi and microvilli. So on top of the villi, there's microvilli. So that's, again, pretty important in the world of absorption of materials in your small intestines. Here it is in the folding of the rough ER, and all of these folds, if you see them all, that allows to increase surface area. So remember, it's jammed inside of a cell, but you have to increase the surface area. The Golgi is also folded. Increase surface area. Now, the plasma membrane, this gets a lot of love. We talked about it kind of in the beginning of the beginning of this chapter. Here it is again. Actually, we talked about it a lot, even in the macromolecule section. The cell membrane has a lot of components, so let's talk about each one. The first is the phospholipid bilayer, and I've talked a lot about this already in the videos prior to this, but that's what a phospholipid looks like. And remember, they're going to run in both directions like that, so that's your bilayer. That is your phosphate-containing head. That is your hydrophobic fatty acid tails. These guys are nonpolar, so they don't like things like water. The heads are polar, and they do like things like water. So for a cell, the polar end, either on the inside or the outside, is in contact with fluids. The hydrophobic tails, not so much. But inside of there, in that kind of tail area, there may be cholesterols, and they're a ring structure. I'll put a C for cholesterol, and they're going to help with keeping the fluidity of this membrane as maybe temperatures get a little bit colder. So let's see what we got. There's your phospholipid bilayer, and again, there it is. This is your phosphate-containing head. This is the polar head. These are your fatty acid tails. These guys are hydrophobic. These guys are non-polar. They not like water. So when water tries to get in here, it, for the most part, most of it gets bounced out. It needs help. And we're going to talk about it coming up in these things called aquaporins. But again, here's your lipid bilayer. So that's your one layer, that's your other. Let's say that this is the inside of the cell. Let's say that this is the outside of the cell. Notice, water's fine there and fine here, but you know water's not getting through. And again, we'll see more of that coming up. Some other components, there may be some cholesterols, which have a steroid base. There may be some glycoproteins, and that's going to be glycoproteins, so a little bit sugar, a little bit protein. You may have a glycolipid. It's going to be a little bit lipid and a little bit sugar. And this whole thing is called the fluid mosaic model because it literally just kind of flows, and all of these components are kind of floating around like pool floats in a pool. So if you look at all these things, we have our glycolipids, we have our glycoproteins, we have our cholesterols right there embedded, and all of these little red dots are your hydrophilic heads, and all of these guys here are your hydrophobic tails. And in there could also be proteins, and they could be what are known as peripheral proteins, which means they do not go all the way through, or they can be what are known as integral or transmembrane proteins, and they do go all the way through. And they could also be channels for letting stuff in or out, the whole facilitated diffusion. Not active transport in this case, but they could also be a pump, which would be active transport. So we'll see all that coming up. Here it is, if you could separate it, kind of like separating bread or a peanut butter and jelly sandwich. We have a lot of things here. We have our hydrophilic heads, which we talked about. Those are those dots. We have our hydrophobic tails. We have our cholesterols. We have our proteins. Lots of different components, but this is what keeps stuff in or out and gives the cell structure. So that's the plasma membrane. A lot of things going on there. Membrane permeability. Well, it's going to let some stuff in or not let some stuff in. So let's see what we're talking about. How does the structure of the plasma membrane influence what is known as selective permeability? I kind of mentioned it a little bit already, but I'll say it again. Certain things can get in easily. Non-polar small things, no problem. Non-polar big things, they'll get in. Things like steroid hormones, testosterone, estrogen. But things like O2, things like CO2, they're small. They're non-polar, easy. They can just go right through simple diffusion. Other things like water, which is small, but it's polar, not so much. It needs help. It needs proteins to help it. Things like sodium and potassium, they're small, but they're charged. They need help. So this amazing plasma membrane, it's going to, again, separate the internal from the outside, which we talked about. We talked all about this already, these phospholipids. And things that are hydrophobic, otherwise known as nonpolar, small things, O2, N2, CO2, gases, freely pass. Water, it's not much bigger than that, but it can't get through because that's polar, and polar things need help, things like protein channels. In the world of water, these protein channels are extremely important. They're called aquaporins. So this is kind of a cool graph. So again, ethanol is small and it's uncharged, so that actually can get through, which is cool. Here's your gases, which we talked about, simple diffusion. Unfortunately, a little bit of water can get through, a little bit, but not much. Most of it does get bounced off. Huge charged things, very charged, amino acids, proteins, whatever. These things, no way, no way, and no way. The only way they're getting through is with some sort of pump or some sort of channel protein, big time. So here's our water, inside and outside, trying to get in or out. And again, you can't really tell what's going which way here. It doesn't matter. In or out, get through with the help of these things called aquaporins. And again, they're going to move from high concentration to low concentration, and that's called osmosis. What is the role of the cell wall? Well, plants have a cell wall. We don't have a cell wall. The cell wall is a non-living carb known as cellulose, and it can be found in plants. Easy. Some prokaryotes and some fungi are going to have, all of the fungi will have it. And what's going to happen is these guys are going to give you a boundary, which is nice, and they're going to let some stuff in and some stuff not get in. So the cell wall, non-living carbohydrate base called cellulose. And if you look, if materials have to get in between plant cells, let's just say, and once again, you know these are a plant cell because it says cell wall, you can see these little gaps, and we'll talk more about this in the cell communication section, but those are called plasmodesmata, and that's going to allow materials to get from one plant cell to another. Nutrients, things like that, water, the little things. A couple of videos on membrane transport and cell size, definitely worth watching. And let's check out our FRQs. Now, a lot of you kind of made a little mistake along the way here. So the first slide that's going to pop up is going to be the answers, which we already went over to the cell questions that were embedded, and then we'll talk about the actual questions themselves. So here's where you guys got tricked. If I look at my first cell has the dimensions of, let's call this 4, let's call this 3, so there's my 4 and my 3, and then let's call that the 1. So this is going to be kind of like a column versus cell B, which is a cube of 2 times 2 times 2. Now, a lot of you, because the formula was screwed up, you messed this up. But let's go through the math when we get up to it. Let's see what we got. So those are the answers to the slides. Once again, I'm sorry I sent the wrong answers. I rounded wrong. I'm very embarrassed about that. But those are the right answers. So make sure they jive. Sorry about what I sent you guys back when I resubmitted your materials. Now let's see what we got. Now, a lot of you did not put this in also into the form of a paragraph. So you got to remember that. All of this stuff has to be in a paragraph form. If it's not, if it's bulleted, if it just looks like some just random stuff, you're not going to get credit. So let's kind of draw my picture again. So let's say that that's 4, that's 3, that's 1. So this is my rectangle, 4, 3, and 1. Again, the units aren't going to come into play because they don't worry about that. So I know that this side is 12, so that's my surface area. But I got one on the other side, so that's another 12. I know that up here is going to be worth 3, and down on the bottom is going to be worth 3. So those are my other two sides. Oh, that's a plus sign. Plus 3. And then I know that this is going to be 4, but I got 2 of them. Plus 4 plus 4. So if you do your surface area math, you're going to get 24, 27, 30, 38 is my surface area. And my volume is going to be 4 times 3 times 1, which is 12. I don't know why it does that. 38 divided by 12. So if I put that in my calculator real quick, I am going to get, let's see, I'll round it right here. So 38 divided by 12. I know it's in my answer already, but I just want you to see it. So it comes out to be 3.16. Now you're saying to yourself, okay, well, there it is right there. In my cube, which has sides of 2, so this looks smaller right off the bat, right? So you got 2, 2, and 2. So my surface area is going to be, I got 4 is the value of one of the sides, but I got 6 of those sides. So my surface area is 24, and my volume is going to be 2 times 2 times 2, which is 8. So now, well, you know what it is. 24 divided by 8 is only 3. So this is 3.16. That's 3. That's close, right? But that's what they could do to you. So cell A has a long and lean configuration compared to cell B, which is a cube. So the longer and leaner cell, even though some sides are bigger, will actually have a larger surface area to volume ratio. The larger that is, that means the more efficiently they will be able to take in nutrients as well as remove wastes. So that is a very, very, very big deal. A lot of you screwed up the math on that. Now, a lot of you here put 4 because of the problem was wrong, which gave you 6, and that kind of messed you up. But I didn't take off of that. That was the fault of A, the College Board, and me, B, for not seeing the mistake with that when I copied and pasted. I mean, really, can't believe that. B talked about how come some things like testosterone and estrogen, which are humongous, they can get in easily. So there's your cell membrane right there. There's your testosterone or your estrogen. They can just simply get right through the cell membrane, no problem. But they're huge. How can they do it? Well, these guys are steroid hormones. And by being steroid hormones, even though they're big, they're non-polar. So it's almost like you know someone at the club. And because they're non-polar and hydrophobic, those things can get in and out of cells very, very, very easily. They pass through with no need for any special channel proteins. Water, although it is way smaller than testosterone or estrogen, it's not getting in. Size is not the issue. Water is polar. And because it's polar, it's got a charge to it. And because it's got a charge to it, it's not going to be able to come and go as it wants. So it needs help from proteins called aquaporins. So for some of you, if you didn't mention that, it ended up being 10 points. I don't know why I put it in as 100. So it ended up being like what it would have been 1 out of 10 or 10 out of 100. So many of you forgot that. But again, be specific. And then the last part here, it talked about the cells of your intestines. A lot of you put spherical. No good. They have to be columns. And then if you said columns, you didn't tell me anything else about it. What I needed you to tell me is that their surface area to volume ratio is huge. And because that's huge, they could absorb materials better. And the reason why that's important in your intestines is, let's say that's your intestines, right? If they didn't have crazy folds or columnar-shaped cells, the food that you eat, it would just pass right through, and by the time it got digested with enzymes, you would absorb nothing and you'd be dead. So the key there is you need all this surface area for the absorption of the materials that came from the things you ate that got digested by enzymes. So with that, hopefully you kind of see how to answer these questions. And again, some of you are doing a great job. Some of you are missing the point here. Maybe you're just answering it without watching the PowerPoints or going through. I don't know what you're doing, but watch and go through the PowerPoint, study it. And if you do that, the FRQs will be pretty simple. All right? So hopefully that was helpful.